Hi, and welcome to the natural logarithmic function integration. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an instructor at Doniana Community College. This comes to us from Chapter 5 of Larson's 11th edition calculus text, Section 5.2, the natural logarithmic function integration. So, we can't necessarily, at this stage, find the integral of the natural log of x. However, we do know that if u is a differentiable function of x, not only is the integral of 1 over x dx equal the natural log of absolute value of x plus c, but in general, the integral of 1 over u du is the natural log of the absolute value of u plus c. Now, this was from definition, and due to domain restrictions on logarithms, right, a log is only defined for positive x values, the absolute value required. This is the most frequently made mistake on exams in my online calculus class is when you have an integral that results in a natural log, do not forget the absolute values. Big time tip right there. And in paperwork also, but websites don't count the whole thing wrong and I have to go back and give partial credit. So I prefer you just get the whole thing right in the first place, and it saves us both a lot of time and effort. So let's find the definite integral, the integral of 10 over x dx. Well, I can rewrite 10 over x dx inside the integral as 10 times the integral of 1 over x dx. I know the integral of 1 over x dx is the natural log of the absolute value of x, so I keep the 10 as a coefficient, and don't forget the plus c, my constant of integration. If I want to find the antiderivative of 1 over x minus 5 dx, I'm going to use substitution. I'll let u be x minus 5, then the derivative of u is equal to the derivative of x. So the integral of 1 over x minus 5 dx is the same as the integral of 1 over u du, which is the natural log of the absolute value of u plus c. We make our replacement. We started with x's, we want to make sure we finish with x's, the natural log of the absolute value of x minus 5 plus c. Don't overthink it. The integral of 1 over 4 minus 3x dx, I'll let u be the denominator, 4 minus 3x. Then du is a negative 3 dx. I don't have a negative 3 extra in my integral, however, I can divide both sides by a negative 3. And when I do so, make sure that's negative, when I do so, I'll end up with a negative 1/3 du, replacing my dx, and 1 over u inside as my integrand. This results in negative 1/3 natural log of absolute value of u plus c, and I reverse my substitution, negative 1/3 the natural log of 4 minus 3x plus c. I don't think I've mentioned it here, but I have this rule, kind of. It's a guideline. I substitute twice. I substitute u to make it easier, and then substitute back to actually answer the question. Indefinite integrals, which we'll talk about here in a few slides, I'll show you what the dual substitution idea looks like. Number 4, the integral of x cubed over 5 minus x to the 4th dx. How do I know u should be 5 minus x to the 4th? Well, first of all, the section we're in, it's the natural logarithmic function, we just learned it, so it's probably going to end up being 1 over u du, but other than that, it's hard to create a denominator with a derivative. It's not impossible, but it's hard. Also, notice that 5x to the 4th, this expression has a larger or a higher exponent than the numerator, and so it naturally leads to, hey, look, that numerator could be taken up in my derivative. And in fact, it is. Du is minus 4x to the 3rd dx. So this x to the 3rd dx and the minus 1/4, right, x cubed dx, if I isolate x cubed dx, divide both sides by a negative 4, I'll have minus 1/4 the integral of 1 over u du. So x cubed dx is replaced by a negative 1/4 du. 5 minus x to the 4th is replaced by a u in the denominator. Of course, my antiderivative is negative 1/4, the natural log of the absolute value of u, plus our constant of integration. And don't forget, the second substitution is replacing u with 5 minus x to the 4th. There it is. There you have it. Now, does it get more complicated? Absolutely. But don't let it be too bad. For the integral of x squared minus 2x over x cubed minus 3x squared dx, when I let u be my denominator, x cubed minus 3x squared, then my derivative is 3x squared minus 6x dx, or I could factor out a 3, and I can see exactly my x squared minus 2x dx that is in my integral. But I don't have a 3, and the technique I usually use is divide both sides by 3, and I'll have 1/3 du equals what I need to replace. Another way of doing that is, if you multiply by 3, so I have this entire expression, I divide by 3 on the outside. So 1/3 times 3, I'm multiplying by a factor of 1. And not a factor of 1, but I'm multiplying by 1. So it's the same thing as if I were dividing by 1/3. The 1/3 du replacing the x squared minus 2x dx. I'm just making this adjustment in one way or the other. 1/3 the integral of 1 over u du becomes 1/3 the natural log of absolute value of u plus c. Replace our u value, and there we have the solution. Do not forget the absolute value. As you're doing these problems for your homework, absolute value is essential. It's absolutely necessary. The integral of 1 over x, natural log of x cubed dx. First, we're going to rewrite the integrand so that we can determine what our u value is. And 1 over x, natural log of x cubed, can be rewritten with the power rule of logarithms as 1 over x times 3 natural log of x. That 1/3 comes out in front. Notice these are all being multiplied together. And so I've switched the order. 1/3 the integral of 1 over natural log of x times 1 over x dx. And here's why. Because I know if I let u be natural log of x, then the derivative of u is 1 over x dx. And this comes through practice. It comes through homework. Practice, 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 so you know what to do when you run into these problems in your later science, math, of course, or engineering courses. So if I have 1 over 3, the integral of 1 over natural log of x, 1 over natural log of x times the 1 over x dx. This is 1/3 the integral of 1 over u du. Something super kind of complex becomes super easy. This is 1/3 natural log of absolute value of u plus c. And of course, we'll reverse our substitution, do substitution twice, once to make the integrand easier, and at the end to go back to the original variable. This is 1/3 natural log of the absolute value of the natural log of x plus c. If we have an integrand that is an improper rational expression, an improper rational expression is when the degree of the numerator is larger than the degree of the denominator, I encourage you to divide as a first step. Use synthetic division, use polynomial division, divide in whatever way you're most comfortable with, but x cubed minus 4x squared plus 7x minus 9 all over x minus 3 has a quotient of x squared minus x plus 4 with the remainder 3 over x minus 3. Now individually, we can find these little integrals using our sum or difference rules. The integral of x squared is x cubed over 3, minus the integral of x is x squared over 2, plus the integral of 4 is 4x, plus 3. Keep in mind that the integral of 3 over x minus 3 dx will have the 3, and then it'll be natural log of u, right? But our u value is just x minus 3, so this is 3 natural log absolute value of x minus 3 plus c. Using the techniques we've had in the first 6 problems, we can find this piece of our integral. So, for integration, learn a basic list of integration formulas. Find a formula that resembles all or part, and then try by trial or error or substitution. If you can't find a substitution that works, alter the integrand. You might try a trig identity, multiplication or division by the same quantity, long division, or if necessary, you could use computer software or graphing calculators that will find antiderivatives symbolically. If you need to, you can use that. So here's the 6 basic trigonometric functions, the integrals. The integral of sine of u du we know to be negative cosine of u plus c. And the integral of cosine of u du is sine of u plus c, and we knew those two. Now the integral of the tangent of u involves a log, as do the integral of the cotangent, the integral of the secant, and the integral of the cosecant. I would like to point out that the secant still sticks with the tangent, the cosecant still sticks with the cotangent. So write in these formulas, know what they are, so that you can use them appropriately. On my website, my UTEP website, you can find a list of some of the basic integration formulas, and these are on them. So if I want to find the integral of tangent of 5 theta d theta, I'm going to let u be 5 theta. Then du is 5 d theta. I don't have an extra 5 hanging out in my integrand, so if I divide both sides, I'll have 1/5 du is d theta. So the tangent of 5 theta becomes tangent of u. The d theta is replaced by 1/5 du, still have my integral. I know the antiderivative of tangent of u is negative natural log of the absolute value of cosine of u. Still have my 1/5 from my coefficient of the integrand, of the integral. And replace u to get negative 1/5 natural log of the absolute value of cosine of 5 theta plus c. If I want to find the integral of secant of x over 2 dx, I'm going to let u be x over 2. Remember, that's just 1/2 x. du is therefore 1/2 dx. Multiply both sides by 2. I get 2 du equals dx. Because my integral of secant of x over 2 dx can now be replaced by, still have my integral, still have my secant. X over 2 becomes a u. Dx is replaced by 2 du. The 2 we move out in front, and the du always stays at the end. And the antiderivative of the secant of u, du, is 2 natural, the 2 comes from in front, the natural log of the absolute value of secant of u plus tangent of u, and finally replace our u values. You can see a very consistent pattern here in how we're finding these antiderivatives using U-substitution. The integral of cosecant squared t over cotangent of t dt. Again, it's really hard to create a fraction a lot of times with a U-substitution, so I'm going to let u be my denominator, the cotangent of t. Also, I happen to know the derivative of cotangent of t is negative cosecant squared of t dt. I have cosecant squared t dt, but not the negative, so when I rewrite the integral in terms of u, I have the negative out in front. This is just the negative integral of 1 over u du. That's negative natural log of absolute value of u plus c. And replace our u with cotangent of t, and we're finished. Now, we have these things called differential equations. And in solving differential equations, it means we're going to find a function y that satisfies these conditions. So, we want to find the equation that passes through the given point. We want to find a specific antiderivative. So the first thing I'm going to do is I'm going to take x minus 2 over x, and I'm going to simplify. X over x is 1 minus 2 over x. And I know, multiplying both sides by dx, I'll have dy equals 1 minus 2 over x dx, and I could take the integral of both sides. The integral dy gives me y. The integral of 1 gives me x, minus 2 is a coefficient. The integral of 1 over x dx is natural log absolute value of x plus c. So I know y equals x minus 2 natural log absolute value of x plus c. I'm given a particular point when x is negative 1, y is 0. So substitute a y value of 0, x value of negative 1. See, absolute values, absolutely necessary. The absolute value of negative 1 is 1. The natural log of 1 is 0. Negative 1 minus 2 times 0 is negative 1. If negative 1 plus c equals 0, then c must be positive 1, and we have our particular solution to this differential equation. If dr dt is the secant squared of t over tangent of t plus 1, and we're at the point pi comma 4, we can rewrite, let u be tangent of t plus 1, then du is secant squared of t dt. In this case, r is the integral of dr, which is the integral of secant squared of t over tangent of t plus 1 dt. And using our substitution, this is the integral of 1 over u du, which is the natural log of the absolute value of u plus c. And reversing our substitution, r equals the natural log of tangent of t plus 1 plus c. But at the specific point where my input is pi and my output is 4, My output of r is 4. Put in pi. I know the tangent of pi is 0 because the sine of pi is 0. So 0 plus 1 is 1. The natural log of 1 is 0. If 4 equals the natural log of 1 plus c, then 4 equals c, and I have my specific solution. Definite integrals. The integral from -1 to 1 of 1 over 2x plus 3 dx. Now here we're going to substitute twice, right? So we'll let u be our denominator, 2x plus 3. Then du is 2 dx, and we don't have an extra 2 hanging out here, so I'm going to call that 1/2 du equals dx, just dividing both sides by 2. My second substitution, I'm not going to go back at the end and put it back in terms of x. What I'm going to do for my second part is up front. When x is -1, I can find my u value to be +1. And when x is +1, my u value is 5. So taking this integral written in terms of x and rewriting it in terms of u, I want to make sure I change my limits of integration as well. It is not true that these should be a -1 and a 1 if I'm using u's, because that's not the appropriate values that we're looking for. So if you're going to switch to u with a definite integral, make sure your limits of integration are also changed in terms of u. 1/2. The antiderivative of 1 over u du is the natural log of the absolute value of u. I'm going to evaluate from 5 to 1, from 1 to 5, but 5 first. 1/2 natural log of absolute value of 5 minus 1/2 natural log of the absolute value of 1. Remember, the natural log of 1 is 0. This gives us 1/2 natural log of 5. The absolute value is a little redundant since 5 is already positive, but I left it in there because why not? It's not wrong. It's just not necessary at this stage. Evaluating the integral from e to e squared of 1 over x natural log of x dx. We had one similar to this a little earlier, so u equals natural log of x makes sense because du is 1 over x dx. Also, when x is equal to e, the natural log of e is 1, so u equals 1. And when x is e squared, the natural log of e squared is 2. So my new limits of integration are 1 and 2 for 1 over u du, which is the natural log of the absolute value of u, evaluated from 1 to 2, which will give us the natural log of 2. You'll see here I didn't use the absolute values any longer because 2 is already positive. Last example, might as well make it a good trig function. The integral from 1 to 2 of 1 minus cosine theta over theta minus sine of theta d theta. With trig functions, which one's bigger? Oh no, there are no powers, but we're still in this section on logarithmic functions. Let u be theta minus sine of theta. Then du is 1 minus cosine of theta d theta, exactly what we have in our numerator. When theta equals 1, u is 1 minus sine of 1. When theta is 2, u is 2 minus sine of 2. We will not use decimal approximations on our limits of integration. We'll use the exact values. So the integral from 1 to 2 of 1 minus cosine theta over theta minus sine of theta d theta is rewritten as the integral from 1 minus sine of 1 to 2 minus sine of 2 of 1 over u du, which is the natural log of the absolute value of u, evaluated. That is the natural log of 2 minus the sine of 2 minus the natural log of 1 minus the sine of 1, using, of course, absolute values. This is the exact answer. If your problem asks you for a decimal approximation, then you would grab your calculator, but until then, leave it. This is a fantastic answer. If you wanted to use the quotient rule for logarithms to condense as a single log, fantastic. But I don't see that as absolutely essential. That's it for the natural logarithmic function integration. Thanks for listening.